Hello and welcome to version B. This is page 1. It's a little bit different from page 1 of version A. So we'll go through this set of approximate pKa values. These are memorization. Ammonia being the most basic on this page is a pKa of 35, so not very acidic. This has a pKa of 10 for ammonium. Acetone has an alpha hydrogen right there that's relatively acidic, has a pKa of 19. Water is 16, and hydronium is 0. Let's then move on to providing degrees of unsaturation in the following formulas. We have right here, we want to add up the number of rings, and pi bonds is a shortcut. We also want to make sure that we have the right number of hydrogens that go along with that molecular formula for following our rules in terms of the fully saturated form versus the hydrocarbon equivalent. And this first one here, at first glance, seems to only have 1 degree of unsaturation because of the one ring, but we can take into account this nitro group over here. And a nitro group has a nitrogen and 2 oxygens. Its Lewis structure is like this. So a nitro group actually adds 1 degree of unsaturation. The total degrees of unsaturation is 2 nitro group. And if you didn't know that a nitro group had that double bond, the other way that you could have figured this out is by counting the total number of hydrogens. There's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You could have counted the total number of carbons being 7, and then an NO2 group. Compare that to its hydrocarbon equivalent, where we subtract the number of nitrogens, meaning this would be an H12 compound, and we ignore the number of oxygens. We compare it to its fully saturated form, which would be C7H16. We can see that the difference between 16 and 12 is 4. That's 2 pairs of hydrogens, and that's where we end up with 2 degrees of unsaturation. So 2 ways you could have done that. Next one, a bit more straightforward. We have 1 ring. We have 2 pi bonds, 1, 2, so that's a total of 3 degrees of unsaturation. We're going to have to do the hydrocarbon equivalent and the fully saturated comparison for the remainder of these compounds. So I'm just going to make a little mini table. And then we see that for a C3 compound, if it was fully saturated, it would have 8 hydrogens. We don't need a hydrocarbon equivalent because it's already there. We're going to compare 8 and 4. We see that there's 2 missing pairs of hydrogens, 2 degrees of unsaturation. The next one, the fully saturated form for 10 carbons, would be 22 hydrogens. The hydrocarbon equivalent, using similar rules that we saw in the first one, would still be C10. And instead of H12, we're going to subtract the 2 nitrogens from the 12 hydrogens. So we get 10. And again, we just go ahead and ignore the number of oxygens. The difference between 22 and 10 is 12, which means 6 degrees of unsaturation for this compound. And then what we have at the end, 9 carbons. We're going to add that number of bromines to the hydrocarbon equivalent, C9H18. The fully saturated form would be C9H20. The difference between the two is only 1 degree of unsaturation, or 1 pair of missing hydrogens. Next, on part C, we're going to draw structures that correspond to these following names. We'll start with this octatetraene compound. There's double bonds on 1, 3, 5, and 7. I think 1, 2, 3, 4, 5, 6, 7, and I drew a couple too many. Okay, we're going to put double bonds between 1 and 2. Another one starting at 3. I'm going to move some stuff. Another one starting here at carbon 5, and the last one starting at 7. We're then going to add the 2 methyl groups, 1 on 2 and 1 on 6. And then we need to make sure our stereochemistry is good. On 3, this is already E. We have the 2 high priority groups on the opposite side of that double bond, so that's looking pretty good. Then we need to look at number 5, and this is for carbon 5. We see we have the 2 high priority substituents on the same side, pardon me, on, on opposite sides. So if we look here on carbon 5, this has the high priority, comparing it to the little hydrogen down there. And if you look on carbon 6, this is the high priority compared to that little methyl group here. So this is not ideal. This is not the way that we want to show this molecule. I'm just going to switch the positions of this methyl group and that allyl group. So we're going to put those 2 carbons pointing up. And that, I believe, was a methyl group. So we have the 2 high priority substituents on the same side with respect to the plane of blue, with respect to the plane of that double bond. So this is now a Z alkene, and we are good for that problem. The next one, we have a pair of 2 heptene, 1, 2, 3, 4, 5, 6, 7, and the double bond is between 2 and 3, or starting on 2, and then a butyl group on 3. 1, 2, 3, 4. And that'll do it. 3-butyl 2-heptene. There's no need to provide EZ designation because we have 2 of the same butyl groups on that same carbon of the alkene. Last problem on this page is to find the functional groups and draw dipole arrows for each bond. We have very specifically an amide group. This is not a ketone, it's not an amine, it's its very own thing, it's an amide. This one here, carbon-carbon double bond, is an alkene. Over here, we have a carbonyl with a hydrogen on one side. This is definitely an aldehyde. And then finally, this is not an aromatic group. That's too general. It's not a benzene ring, even though technically it is. The functional group name is arene. So those are the functional groups. Just erase the circles. And then we're going to look for any polar bonds. This is a carbon-oxygen double bond, which is polar, heading towards that oxygen. We have a carbon-nitrogen one headed here, and you might have put the nitrogen-hydrogen bonds, or dipole is pointing towards the nitrogen as well. So only one main dipole for benzaldehyde, and that is the one of the carbonyl. Once again, electrons being pulled to the oxygen. That's page 1 on version B. We'll see you on page 2.